All right, hello, I'm Quinn. I am in Discrete Math this semester, and this is my final project. I'm going to share my screen, and I'll be drawing with the tablet and clicking through the slideshow, so hopefully everything works simultaneously this time. Okay. So the topic that I chose was statistical paradoxes. So specifically, we're going to be looking at Simpson's paradox, which we will get into. But before we start with that, I want to talk about the history of Simpson's paradox and where it came from and who came up with it. So a brief summary of what it is that Simpson's paradox occurs when groups of data show one particular trend, but then this trend is reversed when the groups are aggregated or combined together. But first, who is Simpson and where did this come from? Edward Hugh Simpson was a British cryptanalyst born in 1922, and he discussed the phenomenon in 1951 in one of his papers, but other statisticians had actually seen it before he mentioned it. Carl Pearson was an English mathematician and biostatistician, and he mentioned it long before in 1899, and Udny Yule, another British statistician, mentioned it in 1903. So even before Simpson saw it in 1922, these other statisticians had seen it before. And then Canadian statistician Colin Blythe coined it Simpson's paradox when he was referring to it in his work. But let's get into what it really is. So we're going to start with an example before we get into the math of it so that we can visualize what's really going on. So our first example is baseball. So for anyone who doesn't know, each baseball player has a batting average. So every time they're up to bat, whether they score, whether they get a hit or whether they don't get a hit, their batting average is the number of hits over the number of up to bats they have. So we're going to look at the difference between player A and player B's batting average. So during the first half of the season, player A has 6 hits out of 24 up to bats. So he has a batting average of 0.250. And player B has 52 hits out of 205 up at bats. So his batting average is 254. So during the first half of the season, player B is better, according to the batting average. And then in the second half of the season, we have 91 out of 291, gives a batting average of 313. And player B has 22 out of 70, which gives him a batting average of 314. So again, player B's batting average is better. But what happens when we aggregate the data and look at the full season altogether? So here we just add across. We have 97 hits out of 315 total up at bats, which gives player A for the year a batting average of 308. And player B has 74 out of 275, which gives him a batting average of 269. So looking at each half, player B has a higher batting average both times, but then when we look at everything together, player A ends up having a higher batting average. So does that make any sense? How does that happen? Let's look at some of the math and some other visuals. Okay, delete those annotations. Okay, so Simpson's paradox really just reflects the fact that our perception of these events can change depending on our viewpoint. So at the first part, we were looking at each individual half of the season, and then our viewpoint changed when we were looking at the season altogether. We can see that the problem is partly with the size of the groups that were being compared, and that aggregating data can change what we see. If you looked at the values for the first and second half of the season, for the total up at bats, the first half of the season, player A only had 24 up at bats, but player B had 205. So we're looking at fractions here, not the totals, which might affect a little bit of what we're looking at. And then even though the data looks one way, when we're looking at it all up together, it changes when we peel it apart. Let's look. So here is one statistics example. So you can see we're looking at regression lines here. So you can see one group, the orange, and one group, the blue, and there's regression lines for each of them. And both of them have a positive slope and a positive relationship. But then looking at them all aggregated together, instead of being split into two groups, there's a negative sloped regression line. So it completely changes based on how we're looking at the data. So we're going to start writing a formal definition, and then we're going to go through and simplify it a little bit. So for a formal definition, we want to start with let n be the number of groups of data. So in our baseball example, we have two. We have player A and player B. And then for each group, there is a set A and B of trials. So this would be like our up at bats during the first half and the second half of the season for each. And with A and B successes, so hits in this case, where 0 is less than or equal to A is less than or equal to A, and 0 is less than or equal to B is less than or equal to capital B for each. Then Simpson's paradox occurs if but when we aggregate the data, so when we look at the full season, then the inequality flips. Let's finish writing that out, and then we can talk more about it. And this is what we saw in our baseball example, and we can get into some more in a minute. So I'm going to clear this and move on to the next slide. So in a more mathy manner, or more the way that we've seen these types of things, we can look at that there exist quadruplets in N. So A, B, C, D, we'll give each one 1 in N, and A2, B2, C2, and D2 in N, such that A1 over B1 is greater than C1 over D1, and similarly, A2 over B2 is greater than C2 over D2. But like we saw, when we add them together, the sign flips, and we have A1 plus A2 over B1 plus B2. And this time it's going to be less than C1 plus C2 over D1 plus D2, which we just saw before. Okay, next slide. Oops. All right. So then, even simpler, pretty much the same thing, just written in another way again. Just A over B is less than C over D, and E over F is less than G over H. But when we add it together, A plus E over B plus F is greater than C plus H. Oops. C plus, no, that's right. G over D plus H, which again is what we just saw. Okay, so let's get into something else. Okay, we're going to look at another famous example, which is at the University of California, Berkeley, where we can talk about some seemingly discrimination with gender in admissions to the grad school. And then when we look at different departments, we might see something else. So we will start looking at the departments all aggregated together and just splitting it up between men and women. So we have men and women as our categories. And then we have the applicants and the percent admitted. And what we end up with is 8842 male applicants and 4,321 female applicants, and 44% of men were accepted, but only 35% of women. So it seems that women are very much discriminated against in admissions, looking at the aggregated data. But what happens if we split it up by department? We'll do on the next slide. Okay, back to annotate again. So we're going to go through each department and see what happens here. Okay, so we have 825 and 108. So in this department, 62% of men were admitted and 82% of women. So women have a higher percentage. Then in Department B, 560 and 25 gives 63% of these male applicants were admitted and 68% of the 25. So again, with the female percentage for this department is higher. Then Department C, we have 325 and 37%, and 593, 34%. So we can see here it doesn't totally follow what we had seen before, where we said that every proportion had to be greater than and then flip it. So we have here, they're not all going to be higher for the women, but we can still see that the majority are. So the same principle still applies. Then in Department D, we have 417 and 33%, 375 and 35%. So again, women win that one. 191, 393, and 28% and 24. So I'm sure you can see the pattern here with which one's highlighted, which one wins, or has the higher percentage admissions rate. And then 272 and 341 gives 6% and 7%. So again, we looked at that our aggregated data, and it showed us something completely different, where 9%, there's a 9% difference in admissions rate for women and men. But then when we look at the different departments, then it shows us something completely different for 4 out of the 6 of them. Okay, and then why does this matter? Why is it relevant? So when we see statistical results in data, we can't always trust it right away. Sometimes there's confounding from other variables, and we have to dig a little deeper to see what we are really looking at. Another thing to consider when we're analyzing data is how the data is being collected. Is it really showing the whole picture? And then this quote here is from Will Corson, a data scientist whose work I was looking at for this project. And he pointed out, thinking causally is not a skill most data scientists are taught, but it's critical to prevent us from drawing faulty conclusions from numbers. We can use our experience and domain knowledge, or those of experts in the field, in addition to data, to make better decisions. Okay, let's see. And then how can we avoid this happening? Or how do we know, if we're looking at data, that this might be an issue? So first we need to consider how data is collected, and then we need to take a second look at disaggregated data and split it up and consider what other information we might be able to get from it. Luckily, if you're using R, then there's a package, Simpsons, that can detect Simpson's paradox for continuous data. But still, this library has some drawbacks since the user has to know where to look and how to specify the independent variable, dependent variable, and the variable that they would like to disaggregate their data with. So it's still a little complicated and it might not catch everything, but it's a useful tool if you know that it might be an issue. So we're just going to look at two other examples. We won't go into detail, but we can look at some other ways that this is applicable. So one thing is that Simpson's paradox can be used to prove opposite political arguments, because as we've seen, we can use the same data and analyze it a different way to prove opposite things. So we can say that women have an advantage in more of the departments at Berkeley, or looking at all of the aggregated data, you can say that men have an advantage because they have such a higher acceptance rate. So similarly, this is Gerald Ford's presidency looking at the tax rates. So you can argue that he raised or lowered taxes because he not only lowered taxes for every income group, he raised taxes on a nationwide level between these 4 years. Similarly, we can look at incomes by education level. So as long as you stratify the data by some high school, some college, and college, in the past 20 years, the US median wage has risen overall, but for each of these following groups, then it has decreased. So we can see again, it's arguing opposite points. So that's all I have. Hopefully you learned something today, and I'm looking forward to watching everyone else's videos. Thank you so much.